Hello, folks. In this lecture, we're going to expand the simple device given to us by the great American chemist G.N. Lewis to include covalent bonding. A covalent bond, as we now know, is the sharing of electrons between atoms. Now, there are some important guiding principles that we need to recognize that determine how the electrons distribute themselves in a covalently bonded system. First, we have to keep account of the total number of valence electrons that are brought to the molecule by the atoms, adjusting this number by any additional or deficit of electrons dictated by the overall molecular charge. A stable molecule will be one in which all the atoms in the molecule think they are in noble gas electron configurations. The atoms want to be noble and have an octet of electrons about their nucleus. The shared electrons in the bonds count toward this complete octet. Covalent bonds are created by the existence of one or more orbitals that have a significant amount of electron density between the two atoms. Do you remember what Pauli said about electron orbitals and how many electrons can go in each orbital? Now, if your answer was 3, you're wrong. Just because this is an orbital formed by molecules rather than atoms doesn't change the Pauli principle. Only 2 electrons maximum can fit in these bonding orbitals, just as in orbitals of atoms. The sharing of the electrons between 2 different atoms usually will not be equitable. Unless the electronegativities are identical, it's more than likely that one of the atoms will be pulling most of the electron density to itself, creating what we call a polar bond. And finally, we must realize that electrons are not static things, and that it's possible for the bonding to move, creating what we envision as a rhythm, a resonance, as the electron density sloshes back and forth across the molecule. This resonance and delocalization enhances the stability of the molecule. Let's first outline the steps we will use to draw the Lewis structure of a given covalently bonded system. Step 1. Count the electrons. Given the molecular formula of a covalently bonded system, we first want to look at the Lewis structure of each of the atoms and then count up the total number of valence electrons or dots that each atom will bring to the molecular system. In the case of a polyatomic ion, we will add electrons to the total for each negative charge on the ion, or subtract electrons from the total for each positive charge on the ion. Step 2. Arrange the atoms. Write the chemical symbols of the atoms in a skeletal structure or arrangement which shows how the atoms might be bonded to each other. In most cases, we'll know the arrangement or can make pretty informed guesses. If we aren't familiar with the molecule, a few rules can help guide us to this proper arrangement of atoms. Hydrogens are usually on the outside of the molecule and not central atoms. The less electronegative element is more times than not the central atom of a simple molecule, and atoms tend to arrange themselves in a symmetric way around the central atom to minimize crowding. Step 3. Create single bonds between atoms. Form connections between each atom pair in our rough structure by placing 2 electrons, which signify a single bonding orbital between each bonded pair of atoms. Step 4. Distribute the remaining electrons. Count the number of electrons used to create these single bonds first, and subtract that number from the total number of electrons we computed in step 1 to create our structure, and start placing these remaining electrons around each atom until you get a total of 8 electrons around that atom. The atom is sharing the electrons in each of the single bonds, so the 2 electrons in every single bond that the atom is participating in also are included in the 8 around that atom. Continue placing electrons around the atoms until you run out. Remember, hydrogen atoms will only require 2 electrons to complete their valence shell, not 8. Step 5. Is each atom noble? If not, you need more bonds. Check each atom and see if it now has an octet, remembering that hydrogen just needs 2 electrons. If all the atoms have octets, then this distribution of electrons and this Lewis structure is a viable solution. If you find that one or more of the atoms don't have a complete octet, you need to add electrons somehow. We do that by going back to step 3, adding an additional pair of electrons to one of the bonds that include the atom that had a deficit. In effect, we are adding an additional bond between these atoms, creating multiple bonds with 2 electrons residing in each bond between the atoms. A double bond holds 4 electrons, a triple bond holds 6 electrons, and so forth. At this point, we go to step 4, redistributing the electrons that are left and not including in the bonds to the atoms that are still lacking octets. We'll repeat the process till we find a possible Lewis structure that has a complete valence around each atom. That's if a solution exists. Step 6. Place brackets and charges on the structures if needed. Just as we did for the ionic compounds, if the molecule has charge, such as a polyatomic ion, we need to place brackets around the Lewis structure. We then place the charge as a superscript on the outside of the bracketed polyatomic species. Step 7. Are there other solutions? Check for resonance. If you can create multiple possible solutions to the same arrangement of atoms or very closely related arrangements of the atoms, then there is a chance that all these structures, though each is distinct, simultaneously exist due to the flow of electrons in the bonds. These Lewis structures could form a set of resonance structures and impart stability to the molecule. All the solutions need to be found. Let's use our new tool to answer a few questions. Why do some atomic elements on the periodic table exist as diatomic elemental compounds and others don't? We now have an answer. These elements make very nice Lewis structures between them. Let me show you what I mean by producing the Lewis representation of the bonding between the atoms in elements that tend to be diatomic gases in nature. We'll first look at chlorine gas, Cl2. Each Cl atom brings 7 valence electrons to the party, giving us a total of 14 electrons. The substance is charged neutral, so there are no additional changes to the total number of electrons. We now arrange the 2 atoms in a structure, obviously a no-brainer for just 2 atoms. We just place them next to each other, but let's not get cocky. This will get a bit trickier later. We place 2 electrons between the 2 chlorine atoms, leaving us with 12 electrons not in the bonding to distribute among the 2 atoms to complete their octets. Now, is each element noble and have an octet? Yes, we have found a solution. Is there any other way to distribute the electrons? Well, probably not, since we only have 2 atoms to worry about in these diatomic gas compounds. The Cl2 molecule is bound by a single bond, and each Cl atom has 3 lone pairs of electrons on it, electrons not included in the bonding. As a shorthand, we can replace the electrons in the bond with a single line to denote a single bonding orbital with 2 electrons. Now, if we're really lazy, we could leave off the lone pair dots, but now it's not a proper Lewis structure. Let's try nitrogen gas, N2. Each N atom brings 5 valence electrons, and N2 is neutral, so we have 10 electrons to work with this time. As in the Cl2 system, arrangement of the atoms and the placement of a single bond with 2 electrons between them is straightforward. Now, this leaves us with 8 electrons to distribute to the 2 N atoms. It's impossible to satisfy both N atoms with octets of electrons with this few number of electrons. So we go back and add another pair of electrons between the N atoms, forming a double bond. In effect, each N already has 4 electrons shared in the bonding. We have 6 electrons left that are not in bonds that we can distribute to create octets around the atoms, but we still come up short. Time to add one more pair of electrons to the nitrogen-nitrogen bonding, forming a triple bond. Now each nitrogen thinks it has 6 electrons, sharing them in the bonding. We have 4 electrons not involved in bonding to distribute around the 2 atoms to complete the atomic octets. Hey, we did it. The result is that the atoms in an N2 gas are bound with a triple bond containing 6 electrons, and each nitrogen atom has 1 lone pair of electrons associated with it. As you might imagine, this triple bond in the N2 molecule probably is a stronger bond than the Cl2 single bond. Let's look at some of the evidence. For N2, the distance between the N atoms is 110 picometers, while the Cl atoms are 199 picometers apart in the Cl2 molecule. We also know that it takes more than 3 times the amount of energy to tear apart the N2 molecule in comparison to the Cl2 molecule. And lest we forget, nitrogen gas makes up 70% of our atmosphere. This is no accident. The N2 molecule is very stable, and now, using the Lewis structures to tell us something about the bonding, we can understand why. Not a bad start. In the next lecture in the Covalent Bonding series, we'll look at some of the more interesting molecules and tackle the question of why some groups of atoms like to carry a charge with them. We know these as the polyatomic ions. See you soon.